35 minutes or 40 minutes.
Okay. Okay, recording has started. Okay, so Pritesh and Sandesh are online. So we were having a conversation about the homework for those who joined late. And I was describing what the scaling is supposed to do. I'm going to start sharing. Okay, so let's say I have some data which is in the range of, let's say, 1 to 10, right? And I have numbers like 1, 1, 1, 1, 2, 5, 10, right? And I want to map these onto a range of 0 to 1. So from 1 to 10, I want to reduce it to 0 to 1. But I want them to have the same properties as what we had out here, right? So one is I can just say, oh, divide everything by 0.2, right? This is not a good example. I'll come up with a better example later. Okay. But the main idea is what we need to do is calculate the mean and the standard deviation for these set of data, right? And basically for each one of these, I'll say x minus mu upon sigma, right? So x gets mapped to x minus mu upon sigma. That's the technically correct way, and that's what the scaling, the standard scaler does as well, right? Okay, but anyway, so I guess Ritesh, you did it. You implemented that. What were your observations?
Me?
Ah,
The outcome of that.
yes. Oh, sorry, Rakesh.
So what I concluded is if you go with the accuracy,
Hmm.
if you without scaling, it is 0.81, which is for the wine data set.
Yeah.
And if you go with accuracy, it goes to 0.94.
Ah, so big jump.
Big jump.
And why?
Yeah, because of that, the scale of the input, maybe the data.
Yeah.
Data set.
Yeah, exactly. So there are some features that are very that have a very big range, and they dominate the distance calculation. But then when you scale it down so that all the features have the same scale, then the true distance can come out, right? Okay. Anyone else? Any implementation questions, homework questions, or questions about the last 2 weeks? Any questions about what we've covered?
I want to understand, let's say, for KNN and for perceptron, I understand spam or not spam. But what are some practical examples of KNN?
Very few actually. So KNN is more as a starting point to get you warmed up with machine learning. There's very, no, and it's also like a quick and dirty kind of implementation. It's very easy to do, but practically you would not use KNN for the main reason being, well, okay. So what is the chief distinguishing aspect? So we talked about classification versus regression, right? What's the other dimension along which we can classify these algorithms? It's parametric versus non-parametric. Okay. And KNN is what is called a non-parametric because we're not doing any training in KNN. We are directly testing it. Right? In KNN, we take the data set, split it into train and test, and then we directly just do the testing. There's no training involved, right? So there are no parameters that we calculate. When we ship the model to clients, right? We are shipping the entire training data set. And a run of KNN is saying, Acha, for this input, calculate the minimum distance with every point in the data set and give me the minimum, right? So that is non-parametric, right? Whereas perceptron is parametric. you will ship the W1, W2, W0 that you've calculated. You're not shipping the entire data. So those parameters are what we are learning in the training phase, right? So now you can use that to say, okay, where would I use something like KNN? So the cost of training for KNN is how much? How much compute does it require? In the training step for KNN, how much compared to perceptron? Zero. We're not doing any training at all, right? Whereas for testing or when you're actually deploying it, how would you compare the compute cost of perceptron versus KNN? Or 100% is the compute cost. When you're testing it, when you've deployed the model, so let's say I've deployed a KNN model and a perceptron model, right? Some new data comes in, I want to classify it. So which model would require more computation? Why? No, perceptron, we would just say W0 plus W1 X1 plus W2 X2. That's the only computation you'll do. You've calculated W0, W1, W2 in the training phase, right? And then in your deployment, some new X1, X2 comes in, we just calculate this equation. And then we say, is this plus one or not? Whereas for KNN, for every point in the data set, we are calculating distances, right?
Still, I'm thinking how it could be used in the real world.
No, hang on. So this is still at the level of mathematical modeling. The point I'm trying to make, what Rohit was asking. So if I look at the computation during training and let's say deployment. Okay. For a KNN and for a perceptron. For training, KNN is 0, right? For deployment, we've got to do distance calculation over all endpoints, right? For a perceptron, we've got to do something to calculate W0, W1, W2, right? Which requires a bit of, we saw the algorithm last time, right? But for deployment, we just have to do this computation, right? So now coming to what you were saying, do we, when would we use KNN? So from a computational perspective, you would say that, if I want something out there immediately, and I'm not worried about the computation cost during deployment, use KNN. Don't spend time in, doing all of these. You're not doing anything in the training, right? On the other hand, if you say, no, speed is critical during inference, during deployment, right? And I'm willing to do some work upfront in order to get that speed. That's when I would say, okay, let's use I was going to say SVM, but let's use perceptron, right? Now, this is only one dimension that you can consider. The cost of compute during training and deployment. The other thing would be to say, okay, let's think about the data itself. Let's understand the data. If it is linearly separable, maybe perceptron is better. Or if it's not, then maybe KNN is better, right? And there are other algorithms as well, which we'll get to, right? But broadly speaking, from a practical perspective, you won't use KNN at all, right? Like from an actual real life perspective. Because just imagine, like if you have a data set with thousands of points, right? Not only is a compute expensive, but even storing the locations of 1,000 points versus just storing one array of W's. It's completely different, right? Okay. Yeah, Sandesh.
So is it because of the scaling that we do in the perceptron? That's why it is taking more computation. cost?
During the training phase?
Yeah.
No, the thing is, so if you look at the algorithm for training the perceptron, right? That is an algorithm that is designed to calculate the values of W0, W1, and W2. Right?
Right.
So that requires computation.
Okay.
Right? So speaking of that, did you guys look at I pushed some code for perceptron. Did you guys try that out? Okay, let me just share my screen. Let's see. Oh, there we go. Okay. So so let me know if you want me to go through this code line by line, or so first I'll just show you the outcome. So basically, I load the iris data set, and this cell has the main perceptron update rule. Okay. Should I increase the screen size?
I'm good. I can see.
Okay. Rohit is like zooming in manually. Okay. Okay. So yeah, this is the main loop. And if you look at it, it's extremely simple, right? It's just saying whenever the sign of so W dot X is the W transpose X that we talked about. L is the label. So if their product is less than 0, that means it's misclassified. And if it's misclassified, we just go ahead and apply the update rule, right? That's all that it is. And then of course, there's a little bit more out here. And then I continue doing this as long as something has been updated. Once I go through all the points with no updates, that means nothing is misclassified, and I just stop, right? And so you can see there are these 5 updates, and these are the lines, as they're shifting. And there's a little bit of an animation out here as well. So you don't see okay, there we go. So it kind of bounces around and finally settles. Even out here, so because, it's reached a midpoint, but then I go through and I test all the points again. It goes ahead and does one more update until it settles on the final value, right? And this is the final this thing. So if you want, we can go through this line by line, or go through it by yourselves, run it, generate different kinds of data, and see how it works. Okay, so what do you guys want to do? Go through the code, or do it offline? Do it offline, and then if you have any questions, just ask. Okay. Yeah.
You have written the actual logic of the perceptron.
Yeah.
Basically.
Yeah.
So do we really need that? I mean, just for understanding purpose, how it actually algorithm works.
Yeah.
Right? But sometimes it may require when we actually trying to customize it.
Yeah.
Is that the purpose of that?
So okay. So here's this. Now this is a very personal. So the answer for you is going to be different than for Rohit than for Amol, right? So it depends on what you want to get out of the course, right? So if you want to say that, oh, I want to go in and start writing my own ML algorithms or implementing my own ML algorithms, then yeah, you need to get into the code, right? But if you say that, look, I need to understand how the algorithm works, right? And and maybe like for this, for example, you can step through it and see how it's going through every iteration. If you're happy with that, so that you understand what it works, you understand, what are the nuances of the code, then you don't need to go through step by step, right? So it depends on what you want to this thing. So, and that's why, like normally when I'm working with students, it's like, here's the algorithm and now you implement it, right? Because that's what they are looking for. For this group, it's more of you guys decide how you want to engage with it, right? Okay. Okay. So now what we're going to do, I am going to, so what I wanted to do was kind of take the SVM or take the perceptron and logically follow down that path. The other thing we could also do is talk about regression, which is what we were talking before the class started. Do you guys have a preference, or what do you, or they're both the same? Okay, I'm going to take an executive decision to go with SVMs. So that's what we'll do. Yes. Yes. Okay. And I'm actually going to talk first about a little bit of math. There we go. Okay. So the motivation for SVM is actually something that Rohit mentioned last time, in that I have a data set like this, right? And I'm trying to do a classification, right? So I'm trying to find the separating hyperplane, and then sure, I can come up with one, right? But then I can also come up with another one, right? Which is equally correct, right? I can actually have an infinite number of separating hyperplanes, all of which are correct for this data, right? And then the question is there some sense of one being better than the other, right? So that's what kind of the motivation for SVMs, right? We're going to see there is in fact a way of defining the best hyperplane amongst all of these. But before we do that, we need to do a little bit of math, right? We haven't talked about dot product, so let me talk about that first. We've kind of touched upon it. Okay. So I have U and V. Out here, I've said they're two-dimensional vectors. They could be any number of dimensions. Tell me when it gets too cold. And I'll switch off the AC. You guys are comfortable. Yeah.
What is SVM you are referring, Srirang?
We'll get to that. So it stands for support vector machine. I just
Okay.
Yeah, I need to do a little bit of math before getting into the
Okay.
SVM, right? Okay. So what is the dot product of two vectors? So algebraically, right, or the mechanics of what we do is basically I take the pairwise product of each element, right? So if U is U1, U2, V is V1, V2, I say U1, V1 plus U2, V2. That is a dot product. And if I have n dimensions, it will be U3, V3 plus U4, V4. I can also write that if I want mathematically as the summation of Ui, Vi, I going from 1 to n. Right? So that's a shortcut way of saying. Okay. In terms of vectors, right? Our vectors are always column vectors. So I will either say U transpose V, which takes a column vector. A transpose is basically rotates it by 90 degrees. It interchanges the rows and columns, right? So instead of this column vector U1, V1, U transpose will be this row vector. It has one row and two columns. Normally the column vector has two rows and one column, right? So I go from a vector that is 2 by 1 to 1 by 2. The shape of the vector is changed. I interchange the rows and the columns, right? And then I do the multiplication by basically saying U1 into V1, U2 into V2. That's how we define the dot product. We will extend this to matrix vector and matrix multiplication as well. But basically, I go along the row and I go down the column and I multiply each element as I encounter them, right? Okay.
Do we really need to transform those? Like from.
You mean U transpose?
Yeah.
Yeah, yes.
Why?
You'll see why. when we come to matrices, so actually a vector is a matrix where one dimension is one. So this dimension is one, or this dimension is one, right? So you'll see why that is when we come to that. Okay. And then of course, because it's UI, VI, I can also say VI into UI, right? So I can also say V transpose U instead of U transpose V, right? Okay. The key thing to note out here is that this product, U1 V1 plus U2 V2 gives me a single number. So it's a scalar value, right? Okay. Okay, so this is the algebra, right? And this is like me just, declaring that this is how we are going to define a dot product, right? We're not going to go into the why of it. It's very interesting, but let's keep that aside for now. But I do want to talk about how to interpret the value that we get, right? So out here, I've made a note that U and V are unit vectors. I'll talk about what a unit vector is. But what that means is, what the implication of that is that the dot product of two unit vectors is going to be a number between 0 and 1, always, right? And very importantly, remember what was a vector? It was a point, in this case, in two-dimensional space. So if this is my space, let's say this is U and this is V, and these are my vectors, right? So if U dot V is 0, right, that essentially means that only happens when my vectors are perpendicular to each other, right? So if they are at right angles, their dot product is going to be 0. Okay? If their dot product is 1 or -1, it means that they are pointing in the same direction, right? So 1 would be, this is V and this is U. -1 would be it's pointing in the opposite direction, right? Okay. If you want to go a bit deeper, it's basically, the dot product of two unit vectors is cos theta. Theta is the angle between the vectors, right? So this is theta, right? And theta is a function that goes between 1 and 0, right? So when the angle is 0, cos theta is 1. When the angle is pi by 2 or 90 degrees, it is 0. I'm just mentioning this here. We'll see it come into play quite often later on. There are times when we want to look at the similarity between two vectors, right? And the similarity that we were talking about before class started was saying that, oh, what is the error, right? So we were taking that y1 minus y2, but then we'll also be taking its square, right? And then we'll be adding all of that up. So that gives us something, like a error term, right? How far away is our estimate from the actual value? There are times when we use these vectors to define certain things, right? And then we say, how similar are these vectors, right? So when we want to calculate that, we'll actually be calculating the dot product, because cos theta or the dot product is something that gives us how similar two vectors are. Are they pointing in the same direction or are they pointing in different directions, right? We'll get to that. I'm just mentioning it right now. Okay. Now, what did I mean by unit vectors, right? So a unit vector is basically a vector with length 1. That's it. Okay. So for example, if I have my vector u at 1, 1, right? So this is the vector I'm talking about, right? What is the length of this line, of this segment? √2, right? Why? Because this length is 1, this length is 1 because of these values, right? It's a right angle triangle, so this length is √2, right? So now if I just take u and I divide it by √2, right? What I'll get is a line out here, and this length will be 1, right? So try this out. So let's say I say this V is U divided by root 2, which is 1 by root 2, 1 by root 2. What is 1 by root 2 squared plus 1 by root 2 squared? Right? So if I take any vector and I divide it by its length, I get a unit vector pointing in that direction, right? So now going back to our original thing, u dot v is cos theta. But u and v may not be unit vectors. I can convert them to unit vectors, right? How? I'll say u divided by the length of u into v divided by the length of v, or this dot product gives me cos theta, or u dot v is the length of u into the length of v into cos theta. Okay? Everyone okay with this? At a high level, you don't have to go into too much detail. A couple of takeaway points that vectors have direction as well as magnitude, right? There are times when we only care about direction, right? I've actually got another notebook that goes into a lot more detail, but in the interest of time, I'm not going over it, but it is on GitHub. Go through that, right? So I'm only interested in the direction. So how do I isolate the direction aspect of a vector? I divide it by its length. And that will be a unit vector in that direction. And then I use that however I decide to. Okay. Now, there's another couple of things that become very interesting. Yeah, here, this sheet called unit vectors that goes into a lot more detail on what I've just talked about, right? Okay. So the other thing that I want to talk about is when I have the separating hyperplane, right? In perceptron, it gives me a separating hyperplane. I can ask the question, and there's a reason for this. What is the distance between a point and the hyperplane itself? Okay, I want to know how close is the hyperplane to a certain point, or how close is the point to the plane, right? The question is, how do I calculate that, right? Again, I'm not going to go into too much detail, but all the details are in the sheet. We can talk about it later on if everyone's interested. The important thing is that distance is basically W transpose X divided by the norm of W, which basically means my hyperplane is defined by W, right? X is the point that I'm interested in. If I take the dot product, W transpose X, right? I get the distance of that point from the hyperplane. Except, now here is the reason why we want unit vectors. If W is not a unit vector, right? Let's say W was 1, 1, right? It defines this line. This is the line 1, 1, right? But this is also the line 2, 2 and the line 3, 3, right? Because they all lie on this line, right? So now if I use W equal to 3, 3, my W transpose X is a different number than if I use W equal to 1, 1, which is a different number from if I use W equal to 1 upon root 2, 1 upon root 2, right? So out here, I want to normalize my W the way we did standard scalar for KNN, right? And we can use standard scalar not for KNN, but for lots of other things. We want to normalize everything so they're all on an equal basis, right? So when I'm evaluating different W's, I'm not going to use the actual W, I'm going to use the unit vector that describes W, right? And as long as I use the unit vector, right, this part, this W divided by norm of W is a unit vector, and I take the dot product of that with X, it turns out that is exactly the distance between a point and my plane. Okay? Okay. So that's the mathematical kind of foundation that, that I wanted to start out with. There are many ways of interpreting dot product. It's, you know, it's also the, and we will be talking about this. If I have two vectors, right? So let's say this is one vector and this is another vector, right? The dot product of these vectors is also the projection of this vector onto this, right? So if this is 90 degrees, right? So this becomes the dot product of U and V. We'll see why later on, and this is incredibly useful. We'll be using it a lot later on, but we'll get to that when we get to that, right? But anyway, so dot product W transpose X, we've seen that when we looked at perceptron. What we introduced today is that assuming W and X or U and V or whatever are unit vectors, that is also equal to the cosine of the angle between the two vectors. And we don't need to, even if you don't remember trigonometry, that's fine. What you should remember is it tells us how closely aligned the two vectors are. If they're pointing in the same direction, their dot product will be 1. If they're pointing in orthogonal to each other, then their dot product is going to be 0, right? And basically a dot product of 0 means that the two vectors are completely independent of each other, right? So the projection of, let's say this guy on the brown vector is 0. You can see that visually as well, right? Whereas if you have a non-zero angle between them, then the projection is whatever, if I draw a 90-degree line, that's going to be my projection, right? But anyway, coming back to what I was saying, so we introduced a new interpretation of the dot product, right? And we said that, okay, in order for this to work, we need to divide the vector with its length in order to get the unit vector, right? And we use that in order to say, okay, if I have a plane or if I have a line and I have a point that is not on the line, what is the distance of that point from this line? Very easily calculated by calculating the dot product. That is a key idea that you've got to take away from this, right? Okay. Now we go back to the problem with perceptron. And in that, what happens is I have my many possible separating hyperplanes. And from the algorithm that we had, the algorithm could give us any one of these, because we start out with a random W and we just keep going, it could give us any one of these, right? Now, the key thing to remember out here is that it is assumed that the test data that we have, or if we deploy this as a model, right, the data that we will be checking this on is going to be from the same distribution that the training data is from, right? So in that context, if I were to take a separating hyperplane like this, right, it is possible that I get a point that is, very close to this guy. Maybe I get a point that is out here. Maybe, right? It's close enough to all the other purple points, but it falls on the wrong side of the separating hyperplane, right? So intuitively, we would say that, even just looking at this, sure, it separates the classes the way we wanted to, but it doesn't seem to be doing a very good job of separating the classes, right? In contrast, okay, we'll get to this. If I had a hyperplane that was like this, right? This seems to be kind of better, right? But how do we quantify that seems to be? Like, why do you think the yellow solid line is a better separating hyperplane than the brown dotted one?
It's not equidistant from.
It's equidistant from both the classes, right? That's absolutely right. And that is what we are looking for. So, so how do we calculate equidistant? So we need to calculate distances. How do we calculate distances? W star X, W transpose X. We take the dot product, right? Okay. So what we can say is that for this particular hyperplane, right? If I take this point, right, versus this point, right, which is more important to me? 1 or 2? Okay, 1 2. Shruti? 1. Ram? Amol? 2. Okay, so we've got a two-way tie. What about you guys online? Is 1 more important or is 2 more important?
1.
Okay. Pritesh says 1. So now, Sandesh, do you want to go with 2? So we'll maintain. Okay, so why? So for the guys who said 1, why? For the guys who said 2, why? Okay, so
If the line moves around, then there would be this, I mean.
Oh, very good.
it should be wrong, right?
For 1.
For that point, yeah.
Yeah, yeah. For the guys who said 2, why did you say 2?
Because when you calculate the dot product, it might happen that it will just not be equidistant from that.
Not be equal. Okay, so we're not even talking about equidistant right now.
The more farther the point
Yeah.
was,
Yeah.
the plane will move.
If it is misclassified. But in this case, it's correctly classified. Right? So it goes back to what you were saying in that if a point is far off, right? Or for points that are further off, they don't care. Right? But for the point that is very close to it, it's very sensitive. A slight change in the plane will result in that being misclassified. Right? So what we are interested in is indeed the closest point, not the farthest point. Right? And then we want to look at, okay. So we have a greater confidence in the point that is far off than the one that is close by. Taking what you said and inverting it, right? Do you see that? If it's close by, then yeah, it is on the right side, but I'm not completely sure. If it's further off, it's comfortably in that this thing, right? Okay. So what I'm going to do is I'm going to look at the distance of every point to the plane, right? And then I'm going to look at the minimum distance, right? Because that is the one that I have least confidence. And then I want the hyperplane that maximizes this value. Okay. I'll go over it step by step. Hang on. Okay. So I thought I'd written it out. Anyway, I'll write it out. Okay. So I'm going to say for each point, calculate the distance of the hyperplane to the point. Okay. And then take the minimum of this. Okay. How will I write that? It's the minimum distance between the hyperplane and the x over all x. Okay. For a fixed hyperplane, look at the minimum distance across all points. Right? And now, which is the hyperplane that I want? Out of all the hyperplanes, I want the one that maximizes this. See if you guys can wrap your head around it. We'll take an example, right? Here is, I don't need this. Okay. Bunch of points. Another bunch of points, right? If I take this, right? Just visually, which is the point that is the closest? Which point has minimum distance of h to x? The yellow top one, right? This is my minimum distance for this hyperplane, right? Okay, let me try another hyperplane. Let me try this hyperplane and let me move it out here. Now, what is the closest point? The one at the right, right? And now observe this guy, this distance is greater than the minimum distance for the brown line, right? Therefore, this is going to be a better hyperplane, right? Let me try yet another hyperplane, maybe this guy, right? And maybe I'll move this down a little bit, right? So now, most likely my minimum distance is this, which is greater than the others. right? So if I take one hyperplane, I calculate the distance of every point to that hyperplane. The minimum distance that I get is my, I'm going to define this term, it's called the margin. Okay. And then across all the hyperplanes that I can have, I want the hyperplane that is going to give me the maximum margin. Got it? Therefore, I want to maximize the minimum distance. The important thing to keep in mind is in this, I'm going over all possible points X, and I'm calculating the distance and I'm taking the minimum. And then out here, I'm going over all possible hyperplanes, right? And I'm choosing the hyperplane that's going to give me the maximum margin. Got it?
Our best hyperplane, right?
Yes, out of all possible hyperplanes. So that is the one that we want. So now comparing it with perceptron may, once we got something that had +1, -1, we were done, right? Now we are saying, no, we want to do better than that. And why are we saying that? Because logically, if I have a point that is very close to the hyperplane, right? So there's two things that can happen. One is, okay, let's, I don't know if I have diagrams for this. Yeah. It will, and okay, let me talk about this. So out here, for example, suppose I have, the data, yellow and purple, right? But I have, oh, well, this is actually a different example, but anyway, I'll use this. So I have this one point out. So let's say this is my training data, and in testing, I get this point, right? You can imagine that having the quote unquote best hyperplane is actually more likely to give us good results than just taking any arbitrary what the perceptron would give us, right? And there's two reasons for this. One is, it's basically what I said out here. It's possible that the data is mislabeled. That happens. It's also possible that my input data is noisy. So noisy mane kya? I've drawn this point out here, but it could easily be out here or out here, like a slight variation in position. It's possible, right? So if I take a separating hyperplane that is very close to this point, right? And it shifts a little bit, then suddenly the point is misclassified, right? So in general, if I want a more robust solution, I need to choose which hyperplane to select rather than just taking the first one that gives me a correct 0, 1, right? Okay. Okay, so this is just, I've kind of written all of this out. And then how do we calculate the distance? W transpose X. Now, if you remember the perceptron algorithm, right? We were saying Y into W transpose X. If that is negative, then do something, then update it. If it's positive, it's classified correctly, right? So in the perceptron algorithm, we are already calculating Y transpose X, right? Except out there, we were only interested in the sign. So we were just saying, is it less than 0? Is it greater than 0? Right? Now, of course, we want it to be greater than 0, right? But we want to do this calculation. We want to say, for all the points, calculate this Y transpose X, choose the minimum one, and I want to maximize that, right? Did you guys online follow that? Akshar, Pritesh, Sandesh?
Yes. Yep.
Okay. Pritesh says yes. Akshar will hopefully reply. Okay. Yeah.
If my data points change, then hyperplane will also change, right?
Yes. Yes. So for a different data set, it will change. And that's a very good point, which we're going to come to in a couple of weeks, or maybe next week, or maybe tomorrow. But there is, so actually, so what Amol was saying is, for the people online, if my data points change, then my hyperplane will change. Right? Assuming they change in a way that impact the hyperplane. And this is something that I want to talk about it in more detail, but there's actually a property, right? which there are two things that measure the robustness of the algorithms that we're looking at, right? We had a small discussion about when did we use KNN. The larger context is how do we decide which algorithm to use, right? And out there, what we have to think about is there is something called a bias variance trade-off, right? And what are these things? So bias is specifically this. If I change my input data, how much do my results change, right? And you can easily see, like for KNN, it may or may not matter depending on how well clustered the data is, right? So if I have like a region for Setosa, a region for Virginica, and they're separated, and I get a new set of readings for my training data, it's not going to matter that much, right? But if you look at, I've forgotten which, but I think Virginica and versicolor overlap. So usme, if I have a region where if I include one data point and exclude another, suddenly the result changes, right? So that has a high bias, right? So it does matter. And that is one of the things we use to determine which algorithm to use as well, right? But we'll get to that. But that's an excellent point. Okay. Now, what I also want to talk about is, okay, fine. I'm looking at minimizing the or maximizing the margin, right? Out here, what I have, this blue line is my separating hyperplane, right? So my minimum distance on one side is this guy, and on the other side, it's this guy, right? So you can easily see that, look, that this has, so my margin is determined by the minimum distance, right? How might I increase this margin? I can just shift the blue line down, right? And in fact, if I take the blue line precisely in between the red dotted lines are going through these points. It doesn't look like it. Actually, it doesn't go through this point right now, but it should be like this. And then this guy should be further down. Halfway between these two guys, right? So the ideal scenario is going to be the minimum distance to one side is equal to the minimum distance on the other side, right? Why is that? Because I want maximum minimum distance. The minute I move the blue line up or down towards one or the other, my minimum distance is reduced and I want to maximize it. If I want to maximize it, it has to be between the two red lines, right? So the red lines, and again, I apologize, this, I'll probably have to update the PDF as well. The red lines are lines that are going through the points in each class. Okay? These are called support vectors, not the red lines, but the points that they go through are called support vectors, right? And hence the name, the support vector classifier or support vector machine is called because these are the support vectors. They are determining what my hyperplane should be, right? And visually, if you look at this, you can imagine like if I were to rotate my hyperplane like this, right? Then automatically my minimum distance is going to reduce, right? So let me go back. Yeah. So my support vectors are determining where my hyperplane is. Okay. And what are the support vectors? They are specifically the points that are determining the minimum distance, the margin to the hyperplane. Okay. Okay. So now, yes, they'll always be parallel because that is where you'll get the minimum distance, right? Okay. Okay.
How many points do we use for support?
Well, technically you need just two, one on each side, right? You might have more, but you need only two, but you need at least two, right?
Points.
For the support, no, so the support vectors are the vectors of those points. So the red dashed lines that I've drawn, right? Those are just for visual understanding. The support vectors are not the red lines. The support vectors are those points. These are the support vectors, right? Okay. Okay. Okay, so this is all fine from a high level intuitive understanding, right? But we need to write this, we need an algorithm that is going to calculate this, right? And this is where I'm going to kind of wave my hands a little bit. So we're going to look at optimization problems in general, right? From a mathematical perspective, the general form of any optimization problem is I have an objective function, right, which I want to maximize or minimize, subject to some constraints, right? So that is the most general form of an optimization problem, right? Now, and then of course, because I want to, so suppose my objective function was, let's say, W1 x1 plus W2 x2, right? I want to find the values of W1 and W2 such that W1 x1 plus W2 x2 is maximized, right? So it's easy. I'll just set W1 to 1 million and W2 to 1 million, right? Usse zyada chahiye, I'll set it to 2 million, or I'll set it as high as I want to, right? So that's why we always have constraints. So there'll be constraints like, let's say, 8 W1 plus W2 has to be less than 20, right? Or something else, right? So that's the nature of what we're trying to do. So I have an objective function, and when I say I want to maximize it, there are some parameters whose values I want to find, right? And I want to figure out. So for example, if I have W1 x1 minus W2 x2, right? Intuitively, I want to increase W1 and decrease W2. I don't want to increase both of them, right? But in addition, I will have a bunch of constraints. So I can't randomly just keep putting any values. I'll have a bunch of constraints that I have to, right? So this is like the most general form of an optimization problem. Okay. Right. And there are very specialized algorithms for different scenarios, right? For example, if my objective function and the constraints are linear, right? What does linear mean? I just have x1, x2, x3. I don't have squared terms. I don't have x1 into x2, right? In both the objective and the constraints, right? Then we get what is called a linear optimization problem, or it's also known as linear programming. It's a fascinating field. We are going to be looking at gradient descent, which is very specifically a linear optimization approach, right? On the other hand, I can have an objective function that is quadratic, right, with linear constraints, or vice versa, right? So that becomes a quadratic optimization problem, right? And like I said, the objective can be quadratic, the constraints can be linear, or the other way around, right? The algorithm for this optimization is very elegant. The maths is beautiful, but if we do that, we'll be here for another 4 weeks just talking about that, right? So we are not going to do that, but you will have to go by faith that there is a way of solving this to get the maxima or minima or whatever we want to. Okay? Okay. So let's go back to the SVM and think about what we've been talking about, right? So we want to maximize the distance of, maximize the minimum distance between every point and the separating hyperplane, right? So I can write that as this. Y times W transpose X is the distance, right? So I want to maximize this over all the W's. So the W's are my parameters, right? I want to maximize this subject to W equal to 1, or the norm of the W vector equal to 1. Because otherwise, again, like before, I could just take higher and higher values of W and I'll get increasing values. I don't want to do that. So I put this as a constraint. W is a unit vector, right? How do I calculate W? It's the square root of W1 squared plus W2 squared plus W3 squared. That's the definition of the length, right? That is this guy, right? So I've got a linear objective function and a quadratic constraint, right? This is a quadratic optimization problem. And there are algorithms to solve that, right? Okay. I can also turn this around, right? And write it like this. I want to minimize the length of the vector subject to y w transpose x equal to 1, right? And it turns out this is actually easier to solve than the other form, right? Not only that, that leads to another optimization, which we're going to talk about tomorrow. Okay, everyone okay so far? So what we've done is we looked at a little bit of math at the beginning. We said dot product, unit vectors, isolating the direction. And then we use that to say, how can I calculate the distance between a point and a plane, right? Why were we interested in that? Because for a perceptron, it gives us a separating hyperplane, +1, -1. But in all the possible separating hyperplanes, we wanted the best one, right? So we looked at an intuitive understanding of what best would mean, you know, if they are oriented differently, if they shift up and down. And then we formulated that as, for a specific hyperplane, look at all the distances of every point, take the minimum distance, that is going to be our margin, and then find the hyperplane that maximizes this margin, right? So that was still a little bit of mathematical formulation, but it's giving us a way of identifying the quote unquote best hyperplane, right? And once we do that, then we say, okay, how do we actually solve this? So we formulate this as a quadratic optimization problem, and then we rely on the library to solve that. So what is important is we've got to say, this is my objective function, this is my constraint. And once I do that, there are packages that will do that solution for us, right? Okay. So, yeah. So now I'm going to switch over back to code. And we are going to look at so I'll show you the, yeah, this is just setting everything up. Okay, so out here, this is one machine learning algorithm that we don't write on our own. We just use the library implementation, right? So I have my normal X train, Y train, right? And then I have from sklearn, I have this right here. sklearn.svm, I import something called svc, which is a support vector classifier, right? And then once I have that, everything else is very standard. So I instantiate the support vector machine, the classifier, with a bunch of parameters which we'll go on, which we'll talk about. I call fit on the training data, and then I call predict on the testing data. Okay? Very standard. I calculate the accuracy and I report that, right? And in this case, I get 100% accuracy because my data is linearly separable, right? I can, because this is a straight line, I can actually print out the weights and the bias. So this is the W1, W2, and this is my W0, right? I can actually print that out. Once again, is there someone asking a question on this? It's not, okay. Right, and I can also plot this. So out here, if you see, this is one data, this is another data. These dotted lines are the support vectors. They're going through this point, and they're going through these 2 points, and this is my separating hyperplane, right? And we'll talk about why this point is out here. Is that fine?
The SPM, is it a prerequisite for positron to get the best hyperplane? Because if you don't use SPM, then we will not be able to get the best hyperplane.
Yeah, so I agree with what the last statement that you made, but I wanted to understand what you meant with the first one. You said, is it a prerequisite for?
It's a kind of constant that if you don't use, then we will not get best hyperplane. If you use only positron.
Yeah, so if you look at 2 data sets that are linearly separable, right? How many separating hyperplanes can you have between them? Infinite, right? Out of which one of them is the best. So what is the probability that you'll get the best separating hyperplane out of those infinite? What is the probability? Zero. You have infinite choices. The probability of any one of them is 0, right? So, yeah, so does it help answer what you were asking?
Kind of, but my question is mainly, let's say, if I want to use a positron.
Yeah.
If I don't use SPM,
yeah,
then I won't be able to get the best hyperplane, right?
So that's my point. So the probability of you getting the best hyperplane using a perceptron is effectively 0.
I have to, yes.
Yeah. Right. Now you potentially could get something decent, but it's completely random. There's no way of really specifying that. Right?
So okay, so that will be less accurate.
Well, I wouldn't say less accurate, but it's not a hyperplane that is as good as you would get from an SVM.
So basically, we are trying to find the better hyperplane,
Yes.
which will not raise the question like we were getting in perceptron, like the earlier algorithm. So in short, Amol, this is better solution than the previous one which we did, because there you had a lot of hyperplanes, right? Imaginable hyperplane, but we are trying to get better hyperplane, which makes you feel that, oh, this looks better, right? I think that is the only difference I can see.
So that is one part. The other part
Yeah.
is there is more that is, we'll see how
Okay.
SVMs actually do a lot more than only getting us the best hyperplane.
So maybe what his question is, to be straight, if we don't use SVM, are there any other algorithm which we can use? That's all right.
Is that your question?
My assumption was we can use SVM with imperceptron, or both are completely.
They are different algorithms, right? Yeah, because with SVM, we are implementing that quadratic optimization formulation, right? Perceptron way nahi hai. We're not doing any, all we're doing is check if it's correct. If there's a mislabeled point, adjust the plane, right? So it is an optimization approach, but it's not the quadratic. So the formulation of the problem itself is completely different. And that's something I want you guys to appreciate, and so thanks for bringing this up. So really speaking, if you look at this picture, you can say, this looks a lot like perceptron. I've got 2 things, I've got a separating hyperplane. But think about the formulation, it is so different, right? This is saying that maximize the margin. Right? So in fact, one variant of SVM is, or the beginning part of SVM is called a maximal margin classifier, because you're maximizing the margin, and the way you do that is through that quadratic optimization formulation, right? Which is nowhere considered in an SVM, in a perceptron at all.
So then if SVM is giving us the better hyperplane,
yeah,
then yes, will there be any use case of using the perceptron?
There is. Perceptron will lead us to thinking about neural networks, right? But yes, again, like with KNN, right? Perceptron is more to get you guys warmed up to what possible algorithms there are, right? Now, you can also think of a specific problem that you're trying to solve, right? Because see, in the end, if you want to do quadratic optimization versus the computation that we do for SVM, it is orders of magnitude high, right? So if you're looking for a quick and dirty solution, and you're reasonably certain कि you're not too worried about the accuracy, perceptron डालना है डाल दो, right? The data set that we're doing with Iris is like 150 data points, and the calculation is literally instantaneous. You press the button, वो result आ जाता है, right? But if you go for real world data sets with millions of points, right, you might actually say, you know what, let me just go with perceptron because SVM is too expensive, right? Another thing you could potentially do, and this is not the case with SVM, but a lot of times, so you have more sophisticated algorithms. And so in all of, like for perceptron, we took random initial values and then we started the loop, right? So imagine using the perceptron to come up with a separating hyperplane and using that as the initial value for a more sophisticated algorithm, right? So you could think about using a perceptron from that perspective. So using it to come up with the initial thing and then apply it later on, right? Okay? Yeah.
So in perceptron, we never cared about the hyperplane. We just cared about the polarities.
Yeah, but the hyperplane gave us the, yeah.
But then what makes, like, why are we doing a hyperplane here? Like, what's the significance of hyperplane here? Because now we are interested in the hyperplane.
Yeah. No, hang on. So once you have a hyperplane and you deploy it, you get some test data, right? And then you want to say, okay, is this +1 or -1? What is its label? Who is determining that?
Perceptron gave us already.
Yeah. So it is a hyperplane that's determining that, right? That's the importance of the hyperplane.
No, but why do we want an optimized hyperplane?
Okay, good. Because if it goes back to what we were saying before. If my data is slightly noisy, or if I have a point that's mislabeled, right? This is going to be a much more robust solution than what perceptron gives us, right?
So does it mean that it reduces the noise in the data, or
No,
does it?
it reduces the bias. Going back to what Amol was saying.
Right. A solution that accounts for slight noise or mistaken data points will indeed be much more robust than one that doesn't.
So I think the robust or the better hyperplane is the answer.
Yeah. So the quality of the solution that we have is better
Right.
with an SVM than
Correct.
yeah. In both cases, we are getting a hyperplane.
Right.
But it's a better.
I see why you are not saying or why you are not exactly using the term of best, like Amol was saying. This is the best hyperplane, right? Because it is. So we are having this hyperplane based on whatever training data that we have.
Yes. Yes.
And that's why it's not best, because you in the practical world you're gonna get more positions, right? That to compare, and this would help you give the better solution, like whether it is positive or negative.
Right.
I think that's why you are not using best terminology.
Yeah.
Right?
So one of the things, like as we proceed right now, our classification is just saying yes or no, or does it belong to A or B, right?
Right.
But as we go ahead, we are also going to add in more confidence out there, right? And confidence is going to be quantified. So we're going to say that this is class A with a 75% confidence, right? Or it is class A with I only have 50% confidence that it is class A. Right now, if we use any of these models, perceptron, KNN, SVM, we are happily saying class A or class B, right? But now we will later on add a bit more, we'll actually put in a metric out there that says not just class A or class B, but exactly what is my confidence in that prediction, right?
Right. It again adjusts the
So Amol was asking if data changes, will we adjust the hyperplane? This is what we were talking about last week. it's up to us. As new data comes, so think of it this way, right? So new data comes in and we make a prediction. End of story, right? Now, if the user comes back to us and saying, hey, this prediction was correct or this prediction is wrong, then we can say, okay, let's include that in our training data again, right? And if it is correct, for a perceptron, it won't matter. Hyperplane, it's correct, it's correct. It's not going to make any change. For a SVM, if it is correct, but it is changing the margin because it is closer to the hyperplane than what it was, maybe we will change the hyperplane, right? And then, so last week, that was the conversation we were having, that do we want to take in all the feedback that we're getting, run the entire algorithm on the entire training set plus these new data points, right? Or do we want to take a subset of the points and just refine it a little bit? That is a judgment call, right? That is like, how critical is that accuracy? We also need to look at different metrics of measuring how good an algorithm is. But also, how much time am I willing to spend on the training part to redo this over and over again? That's a judgment call that we've got to make.
So in the, how does it work? Let's say we have this type, we're fetching this.
Hmm.
Then it will, how does it work?
So that's the thing. It depends on your application, right? So I'll take a very specific example. They weren't using SVM. They were using a very different approach. But so in the oil and gas sector, we have these machines called expanders, right? So who has the precious bike? Was it you or Pritesh? Okay, Pritesh then. He's got this bike that he doesn't park in public spaces and stuff like that, right? So, so bikes have compressors. So normally we are used to engines having compressors. Out here we have expanders, and the idea is you put gas in it and you expand it. That cools it down. That's how you make LNG, right? And those expanders are big. They're like as big as this flat, right? And they are super critical that so we don't, if an expander breaks down, it'll affect production, right? So we don't want to have it break down. Plus, it's expensive to repair and all of that. But at the same time, so because we don't want it to break down, there will be scheduled maintenance where we stop production, we check, make sure everything is okay, and then we bring it up again, right? So now out here, assume I have a machine learning algorithm, and this thing has like, it's got like 50, 60 sensors on it. It's measuring everything you can imagine, right? So we have all of this data, and based on the data, we want to say, okay, is it time to bring this down for maintenance or not? Because we want to run it for as long as possible without it breaking down because something went wrong, right? So now you can imagine that for that kind of scenario, right, where it is absolutely critical, right? Every time I get new data, you can be sure I'm retraining my model, right? So that I get the best possible predictions, right? But on the other hand, if I have, something which is saying ki, let's say I'm Amazon, and I'm saying ki this particular client this is his purchase history, and based on what he's purchased, recommend some new product for them, right? So now usme, like if I make something, so this is being run millions of times per second, every time somebody goes to the website, right? So now the question is, every time if the guy accepts my recommendation or doesn't accept my recommendation, if I retrain my model every time, the cost of that will be much more than whatever benefits I get from making that recommendation, right? So that's why I said it's a balance that you have to come up with based on the criticality of your prediction and the cost of retraining, right? If the cost is worth it, do it. If the cost is not worth it, don't do it, right? And then maybe you'll batch, like you'll say, okay, let me wait till I have 1,000 new inputs before I train it. And maybe I'll train it just a little bit. and maybe once a year I'll do a full, I'll take all the data points and train it again. So it's a judgment call, right? And it's always a trade-off that you have to maintain, right? So I won't be going into the details, but one thing I hope to cover right at the end is these CI/CD pipelines for machine learning models, right? Of how you maintain your models and how you update them in real time, right? But we'll talk about it when we get to that point. But it always comes down to judgment based on what you're trying to solve.
Point of this question was, I thought if I gave the data points, the algorithm will automatically take care of that and adjust the hyperplane.
If you ask it to. See, what is the algorithm doing? I have input data, I have my training set, and I'm training the model on that set, right? So now if we say I have more data points, the algorithm is not automatically doing anything. You have to either set it up saying the minute there's a new data point, retrain, or let new data points come in. I will decide when to push that button to train it. It's a judgment call, right?
The output is actually just like the plane, right?
The separating hyperplane.
Separating hyperplane.
Yeah.
So whenever new data will come, it will just check around whether it will be this side or that side.
So that is, so again, you have a training phase and an inference phase, right? Training phase mein it's figuring out what is the best fit for the model. The inference phase mein it's saying, acha, ye input aaya, what is my prediction? Ye input aaya, what is my prediction? Yeah. Okay.
So
Yeah.
in this, why is the red dot?
I'll come to that. I'll come to that. Yeah. And that's one reason why SVM. So I haven't seen this in India, but in the US, like, late at night on all these channels, they used to have these half an hour, 1 hour, 2 hour long things where they were selling stuff. All kinds of crap you can imagine. I've seen it in India actually, the magic bullet mixer, right? And they'll Napto. And the funny thing is, this is like the same video that they show abroad. So they'll have this blonde hair or these very Caucasian looking, and they'll be speaking in Hindi. And it's hilarious to see that. But one standard phrase they have is, but wait, there's more, right? If you buy this and you do it in the next 30 minutes, we'll throw in this for free, right? But wait, that's more. So with SVM, not only does it give you a more robust solution, but wait, there's more. We'll talk about that red dot in this context.
I guess Sandesh has.
Oh, Sandesh, did you have a question?
No, I think yeah, it was old hand raised, but I wanted to understand what Amol asked, so yeah, that's why I read. But
Okay,
but
so
I think I got
it from the
your
context.
answer, like yeah, what you wanted to
Sorry,
answer.
I make it a mental note ki if somebody asks a question, I'll repeat the question for you guys online. But
Yeah,
I
I'm trying to get the question with the
yeah.
captions, but yeah, I was not able to capture his question.
No,
But yeah.
just interrupt me next time.
Yeah.
Don't raise your hand or anything. Just
Yep.
interrupt.
Yep. Thank you.
Okay. Any other questions? All good? Okay. So homework for you is again, so if you look at the code out here, it's actually, I don't know what I'm sharing right now. Oh, I'm sharing the code, right? Implementation wise, it's literally just instantiation, call the fit, call the predict, and calculate the accuracy, right? Okay. If you look at these parameters, right, kernel, C, and random state, right? And so let's start talking about some of this. Okay. Let's see. Okay. So I'm going to go back to my notes. Okay. Okay. So now, if you look at the data set on the right, okay, and you apply SVM the way we talked about it, what will we get? We'll get a hyperplane that looks something like this, right? And then you have the support vectors above and below it, right? But objectively speaking, if I look at this, this one point is very far away from the other yellow points. In fact, it's closer to the purple points. It's possible that that point is mislabeled, maybe, or maybe it's labeled correctly. But I would argue from the perspective of doing a better job with test data, because I'm going to get a lot of purple points that are close to the hyperplane. I might get a purple point that is on this side of the hyperplane, and it will be, the prediction will be that no, it's a yellow point, not a purple point, right? So even for this kind of data, it may actually be the case that this is a better separating hyperplane. Even though that one point is mislabeled in my training itself, I've not correctly classified that one point, right? From the perspective of the other points, it makes sense to have this guy as my hyperplane. Does that make sense? Shruti? Okay. So that's one thing. The other thing is, like we said before, noisy data, your things might move. So I might prefer to mislabel a few points and increase my margin, right? Because larger margin is making me more robust to noisy data, right? Okay, so those are the two motivations out here. So not only am I going for the best hyperplane, but I'm going to say that I will sacrifice a few points if my margin can improve. Okay? Okay. How do we do that? Right? So right now, my formulation is the alternate formulation that I had. So rather than saying I want to maximize Y W transpose X, I'm going to say I want to minimize W transpose W such that Y, so I'm talking about this, right? I want to minimize this guy such that Yi W transpose Xi is greater than or equal to 1 for all the i's, for all the points. Okay? Okay. By the way, notice I said greater than or equal to 1, right? This is a little bit of convenience that I'm using. So let's say my margin is M, right? I can divide all the distances by M so that I get a margin of 1. So it's just, okay. It's just convenience. Okay. But now I'm saying that, okay, instead of enforcing this strictly, right, I'm going to allow, so what this is saying is this margin that I have out here, right, every point Yi into W transpose X greater than or equal to 1 means every point is either on that red line or it's away from the red line, away from the separating hyperplane. That's what it means. Okay. Now, if I'm willing to allow a point to be inside this, right? So it's violating that rule of support vectors. And the reason I'm doing that is because I want a larger margin. Just because I have this point out here, I don't want to have a very small margin. I want to have the bigger margin that I had. And I'm willing to allow that, right? So what I'm going to say is, I'm going to modify my constraint by adding slack variables, right? So I'm going to say yi w transpose xi is greater than or equal to 1 minus some psi I. Okay, psi I is a slack variable. I'm introducing a new thing into this formulation. Okay, now what will this psi I be? For any point that is outside the margin, it is going to be 0. So nothing changes, right? But there might be some point that is inside the margin for which psi I will be, let's say, 0.5. Okay. So even though all points are supposed to be outside the margin, for that one point, it still satisfies this condition because I'm allowing psi I to be 0.5. Yeah, go ahead.
Psi I is the distance between the hyperplane and the slack point.
And the new, so I'm looking at this point, this guy, that violates my, it's closer to the hyperplane than my margin, right? So for this point, psi I will be some value, some positive value, right? For everyone else, it's going to be 0. And we'll see what that value is in a second.
Then, how will I know that the point is falling.
Very good. This is the beauty of this formulation, right? I'm going to say, you'll see how it is. I'll formulate it, and the algorithm, the optimization algorithm will figure out what the correct value of psi is. Okay, it's almost like magic, but it's really cool. Okay?
It's falling on the same side, right?
It's falling on the same side. We look at the opposite side also in a little bit. Okay, but now the problem is I've said minimize W transpose W, right? I need to accommodate this psi I. See, if I say minimize W transpose W, the only thing that the algorithm is going to calculate is the W values, right? But I wanted to calculate the psi I also, right? So I'm going to include, and this goes to what Rohit was saying, and I said the algorithm is going to calculate it. Why will it calculate it? Because I include the psi I in the objective function. Remember, objective function and constraints. I've modified the constraint. Now I'm taking that slack variable, I'm going to put it in the objective function, right? How will I do that, right? So, okay. So I'm going to say, sum up all the slack variables, right? And make that part of this minimization routine. Okay? Let's think about what that means, right? I want to minimize W transpose W, and I'm saying plus psi I, right? So I want to minimize this whole thing. That means I'm trying to minimize psi I as much as possible. And that is a key part, right? Because if I don't put this, then it'll put all the psi i's into the margin. Then there's no meaning. I mean, margin ka koi matlab hi nahi rehta, right? But out here now is going to try to balance these two things, right? On one side, it's saying that, okay, I'm calculating these distances, the W transpose Xi, right? And I want that to be greater than or equal to 1, right? At the same time, and as I'm calculating the W's to minimize this such that this condition is true, right? And at the same time, for the slack variables that I allow, that is part of the minimization. So I want to make that as low as possible as well. So I'm going to allow very few variables, very few points to have a positive psi. Ideally, I would like to have all of them to be 0. Ideally, I would want them to be 0, right? But in case they are not 0, I want to minimize the ones that are not 0. Okay? Okay. What is psi? If y into W transpose X is greater than or equal to 1, psi is just 0. If it is less than 1, that means it's closer to the margin, including if it's on the other side, to what you were saying. I'm going to set it to 1 minus y W transpose. What is W transpose X? It's just the distance, right? So 1 minus that distance. If I plug that out here, 1 minus 1, that goes away. I'm just left with W transpose X. So it's just that distance. That's a value of psi. And we know that W transpose X only varies between 0 and 1. Why? Because unit vectors, their dot product always goes between 0 and 1. Right? So the pieces all fit in very nicely from that perspective. Okay. So yahan tak theek hai? Okay. The basic idea is I want maximum margin. I could have some points that are very close to the other side, so I'll end up with a very small margin. So I want some way of saying that, let them be misclassified or let them be inside the margin. Don't take support vectors that go through this point. How do I do that? I introduce slack variables. And I put those slack variables both in the constraints as well as in the objective function. Okay? Okay. Now, finally, yeah, sorry, was there a question online?
When we say it's misclassified, what does it mean? So we are not
it's on the wrong side of the hyperplane.
Wrong side. So we are just disqualifying them in our hyperplane calculation, right?
We are not disqualifying them. We are allowing them to be on the wrong side.
Okay, but highlighting that it is misqualified.
Yeah. So, for example, what will happen is if you have many points on the wrong side, right, then your hyperplane is not a good hyperplane at all, right? But if you have, let's say, let's say this is my data set. All of these and one X out here, right? And all of my other points, my second class are all out here, right? Now what's going to happen is this point down here is going to decide what my hyperplane is, right? So I'm going to allow that point to be, I would rather have my hyperplane out here than have it out here. Sorry, that was supposed to be a straight line, but you get that, Sandesh?
Yeah.
Right? So therefore, so I'm not disqualifying it. I'm not ignoring it. I'm actually including it because of this slack variable, right?
Right.
And by including the slack variable out here, I'm ensuring that, okay, I will allow one, maybe two, maybe three if I have like, you know, a million points or whatever, or a few, but not all of them, or not like 50% of them be on the wrong side. Does that make sense? I'm making those misclassified points or the points that are inside the margin be as few as possible.
Yep. Got it. Yeah. Thank you.
Yeah. What do you mean either?
Like in that region where now highlighted.
Which I just deleted. Yeah. Yeah, there could be a purple point out there or a yellow cross out here. Absolutely. Right.
And does the number of points in that region define the quantity of points, count of points? Let's say if I have 6 points there and 1 point.
So from a mathematical formulation, it doesn't.
No.
Because so see, yeah. So like if you look at if you look at perceptron, right, it's going through every point. So out there, you might make a case that, oh, if I have 5 out here and 20 out there, then is it? But even then, it won't matter. No, it doesn't. It doesn't. Right? And even from a mathematical perspective,
because it will not calculate color.
Well, it's class that matters, right? Yeah. No, I'm just thinking, and maybe I misinterpreted your question, but I was just thinking if the data set is very unbalanced, would that matter? But it doesn't, because once you write these equations, it's just a straightforward calculation after that. No.
Less data will be less, and it's not linear. Like it is linearly separable. But
Oh, I see what you're saying. So let's say we have only 2 points in each class, right? And out of that, 1 point is on that side. So I would say then, you know, maybe you shouldn't be using any of this stuff.
No, if there are more points, let's say if I have 8 points up and 4 points.
You mean in a class you have 12 points?
No, there are linearly separable points are there.
Okay.
Now the
one class has 8, the second class has 4.
Yeah.
That is okay.
But there are inverted points that are so.
Yeah, so that's the thing, right? So like I said, like if you have 100 points and usme se 1 or 2 are on the other side, that's okay, right? But if you have 4 points, you probably, you know, you probably will just stick with 4 points. You can't even get a good hyperplane because your new data point. Right? So see, okay, here's the thing, and this is kind of a property of your data. Suppose these are my 4 points, right? And these are my other 4 points, right? That's kind of one scenario, right? But now suppose these are my 4 points, right? And these are my other 4 points, right? It's a very, and then if you say, okay, my next, when I test it, my next data point has the same characteristics as my training data. With 4 data points, with this, you can imagine that, okay, I can guarantee that. But with this, probably not. Right? So there's actually, if I take this to the extreme, there's actually something we haven't talked about, but so technically speaking, the points that we have are assumed to be IID. Are you familiar with the term? So they are supposed to be independent and identically distributed, right? And that independent part is very important. So just because I have, points in one region doesn't mean that the next point will also be in that region. That is what independent means. So the distribution of these points, okay, what does identically distributed mean? If these points are sampled from a particular distribution, the test data is also going to be sampled from the same distribution. That's what identically distributed means, right? And that's why if you say that I have only 4 points, that's not really enough to define a distribution, right? And that's why, I mean, intuitively you can say, okay, it's probably not right, but also mathematically, you can't define a distribution with 4 points, right? So for example, the 4 points might have the same value. Doesn't mean that the 5th point will also. Okay, I'll give you a very simple example. Suppose I toss a coin. Okay, what is the ratio of heads to tails that I expect to get? Right, 50%, right? Now, if I toss a coin 4 times, okay, if I toss a coin 50 times, right, and I have 25 heads, 25 tails, that makes sense, right? But if I toss a coin twice, right, the probability of getting 2 heads is actually pretty high, right? It's not guaranteed that you'll get 1 heads and 1 tail. You could get 2 heads or 2 tails, right? Because the number of samples is very low, right? So on the other hand, if I have 50 data points, half heads and half tails, that's reasonable, right? I can expect that the next data point that I have has a 50% chance of being a head or a tail, right? But if I toss a coin twice, right, and I get heads, I cannot claim with a large degree of certainty that I am always going to get heads in the third. I may get heads, I may get tails, right? So you get a sense of where I'm coming from. So that's why, going back to what I said at the beginning, if I have 2 unknown variables, I need 2 equations to solve for them mathematically, right? But in machine learning, we are happy to get more data, because a lot of what we're doing is in the presence of noise, and we are interested in expected values. We are interested in statistically getting the right answer, not accurately getting the right answer, right? Now, there is a flip side that we'll talk about later on, and that has to do with overfitting. If you have too much data, you might end up going in completely the wrong direction, but we'll get to that later on. Okay? Yes. Sandesh.
So I was landing on, just to reiterate, what is the purpose of this calculation, the psi calculation?
Right. So the idea is very specifically, if I have a scenario like what I've shown out here on the right hand side, right? Normally, I would say that my separating hyperplane is out here, right? I'll move this out of the way. Right. For this data, the blue line is a separating hyperplane. Barabar?
Right.
Right. But the problem is, if you notice, the only reason the blue line is so much down is because of this point out here, this yellow point.
Correct.
Now, that yellow point might be there because it's mislabeled. It's actually a purple circle, right? Or maybe it's labeled correctly, but it's an outlier. it's not, it's very unlikely that we get that kind of point given the distribution of these other points, right? Does that make intuitive sense to you?
Yeah, right. This thing I got, but
so
how,
now the thing
yeah.
is, how do I, in my
Yeah.
formulation, right? What was my formulation before? It was this one. Minimize W transpose W such that Yi W transpose Xi is greater than or equal to 1. So this is a very strict restriction.
Right.
Right. It is making sure that every point is classified correctly. There are no misclassified points. Barobar?
Right.
Okay. But now we want to say that, no, you know what? I know that there are scenarios like this. So I'm going to say, let a point be misclassified. Let me select a hyperplane such that a point in my training data set is misclassified. Let me allow that, because the margin of this line is better than the margin if I were to have a completely pure hyperplane. So I'm sacrificing the margin, I'm sacrificing the correctness for that one point so that I get a better margin.
Right.
And how I do that is by introducing the slack variables.
Got it.
Okay. Okay, so just to reiterate, my final formulation looks like this, right? My objective function I'm including the slack variable. And in my constraint also, I'm including the slack variable. What is the purpose of including it in the objective function? My objective function is to minimize something. So I want my slack variables to be as low as possible. What is the point of including it in the constraint? I'm saying 1 minus psi I. Right? So I'm allowing a point either to be misclassified or to be inside. So then it gives me more freedom for the margin. My support vector can belong to a point that is not just the closest point, some other point. Okay? Okay. How do I define psi? If it is outside the margin, then I set it to 0. If it is inside the margin, it is 1 minus W transpose X. And I take the maximum of these two. Right? So it's either 0 or it is the other one. Okay? And now, if I substitute that value of psi I out here, I get this. Right? Minimize W transpose W plus the summation of, for every point, either 0 or 1 minus Y W transpose X. Okay? Okay. Observe, in my formulation above, and I didn't write it out here, I have this C multiplying psi I. Okay. What is this C? So if you think about it, C is a parameter that I'm going to decide. It is a hyperparameter. It is not, the algorithm is not going to figure out C. I am deciding C. Which is the other hyperparameter we've seen so far? Which are the algorithms we've seen so far? KNN and perceptron. Any hyperparameters in these two algorithms? What is a hyperparameter? Actually, it's not perceptron, it's KNN. K, right? What is the optimal value of K? We decide that, right? We experiment and we figure out what value of K to use, right? So similarly out here, we are going to decide what value of C to use, right? And very importantly, let's think about it, right? C is multiplying. So there are two values in this minimization objective function, right? One is W transpose W. Those are the parameters of the hyperplane that we're interested in. The other is those slack variables, right? So C is going to help us figure out what is the relative importance of these two. Okay. So you missed the punchline. So C is a hyperparameter that is going to tell us what is the relative importance between the two terms in the minimization objective function, W transpose W and psi I. Okay. So if I set C equal to, let's say 1 million or some really huge number, right? What will happen? If it's a huge number, it doesn't even matter what we do with the psi I, right? Because Actually, or does it? Actually, no, I take that back. Suppose we set C equal to 0, right? Then the objective function is just going to optimize for W transpose W. But the danger out there is it could put psi I values very high. We're multiplying it with 0, so it's not being accounted for in the objective function, right? So that could be really bad. You could have many points inside the margin, many points misclassified if we set C equal to 0, right? But if we set C to higher values, we are giving more weight to the slack variables than to the margin. You guys get that? So that is the balance between the W transpose W and the slack variables, right? It is a hyperparameter. We have to figure out what we have to do, what we have to set it to, right? If we put lower values of C, if we put higher values of C, we get closer to the original. I'm actually rethinking this. Yeah, it's a minute. No, but between the two of them, W transpose W and the slack variables, right? If you set it to 0, right? Oh yeah, that makes sense. If I set it to 0, right? It'll push more points into the margin, but my margin will be very big, right? But as I increase the value of C, the slack variable importance becomes higher. So we'll try to make that as low as possible. And then it'll be similar to the original SVM formulation. Okay? It depends. We've got to play around with it to figure that out. Because see, for a multi-dimensional data set, we may not be able to just look at it and say, oh, there's this one point that is out here. Because in multi-dimensional space, we can't visualize it. Right? Plus, we might have so many points that is impossible to figure out. Right?
Can we figure out, let's say, from 100 data points?
We'll talk about it. I wanted to cover it today, but we don't have time.
Based on that percentage, we can decide.
No, I'll show you how we can figure that out. Right? Okay, let me just switch to the code very quickly. So if you look at what I did out here, I set C equal to 1. So in this model, I gave it a bunch of parameters. Random state equal to 42, you guys know what that is, right? C equal to 1, that C is this guy. It is telling us how much we want to, how much importance we want to give the slack variables versus the margin in our objective function, right? When we set that, we get this red point inside the margin, right? And this becomes what is called a soft margin classifier, right? So we want a maximal margin classifier. Soft margin classifier is going to allow for some guys to be inside that margin, but we still want to increase, because otherwise this would have been one support vector and this guy would have shifted down, right? And our margin would have reduced. But by allowing this point, we've got a larger margin. Okay?
If C equals to 2, then?
Let's try it out. So what did we say if C is equal to 2? Or why 2? Let's set it to, where did that go? Yeah. So the accuracy is still 100%. I don't know if this changed, but oh my God, none of this is run. Okay. Torch. Oh, so nothing ran. Okay. Yeah, I ran it before, so okay. Okay, so right now accuracy is 1. It's still 1 as expected. This guy, let's see if these change. Yeah, they did change. And now if I visualize this, there you go.
That point becomes now
The vector, the support vector, right? And of course, we saw with one, it was actually, this guy was the support vector, and this guy was mislabeled, or it was inside the margin rather.
So one is not really, and C is not really the way how many counts, right?
No, no, no.
You have to understand the exact.
So if you looked at the formula, right, the objective function was minimize W transpose W plus C times the sum of the slack variables. Okay. So C is basically being an arbiter between the two of them. If C is equal to 1, it means they are both equally important. Okay. If C is equal to 0, right, that means go crazy with the slack variables. I want maximum margin. So what will happen? Everything will be inside the margin. Let's try that. Right. So C is basically balancing between these guys. I don't know. Let's see. Okay, yeah. So let's give it maybe 0.001. Right. It's still got all of this is fine, but what I really want to see is the figure. See, everything is inside the margin. Right? Because you're saying, the slack variables go crazy because I'm multiplying it with 0.001. So even if that value increases, the multiplier is pushing the value down. So what becomes more important is the margin, the W transpose W. I want to minimize that. And that gets us this. Right? And on the other hand, if I set it to 2000, then the slack variables become very important. And because we want to minimize them, we'll make sure that there are all slack variables are 0. And there's nothing inside the margin.
Is there an optimum C? If I put 85, for example,
Yeah.
will it give the same result as 2000?
Try it out. Code is there. No, the thing is, to your question, right? Is there an optimal value? First of all, it depends on the data, right? It depends, like the example that I had, there was one guy that was way down here, right? That's one thing. The second thing is, it also depends on what you're trying to achieve, right? So now when you get your test data, right? Depending on what value of C you have, you're going to get different accuracy results on that test data, right? So now you've got to again play that game saying ki, how should I arrange how do I experiment to get C so that my test, but then I don't want to use my test data to figure out C. So how we do that, we'll talk about tomorrow. Yeah. You cannot visualize it. Yeah. Yeah. Okay. Okay. Let's stop out here. I wanted to talk about like the validation set, but we'll talk about that tomorrow. We'll start with this tomorrow, and we'll talk about the kernel methods. So if you look at this call, the other parameter out here it said kernel equal to linear. Yeah, kernel equal to linear. So I want to talk about that. And that is the other very, very powerful difference that where you can extend support vector machines in directions that you cannot with perceptron. Right?
Is the kernel related to graphics?
No. No, it's not. Yeah. Okay. Any questions online?
No, sir.
Okay, your half an hour, 20 minutes to half an hour became 2 hours. Okay, but so tomorrow 7:30 morning. Yeah. Okay, thanks guys.
Thank you, sir.